This video is about z-scores. This involves transforming a variable. A transformation is the replacement of an existing variable with a mathematical function of that variable. The essence of a transformation is basic maths. However, we need to cover it in the context of statistics because transformations are frequently used, and so it's important to understand why and when they are used and how to interpret them. So we're going to talk about z-scores. Their creation involves what's called a linear transformation, so it's worthwhile understanding a bit about what this means before we go on to specifically cover z-scores. So linear transformations are often used to change the units of a measurement. A simple example is changing grams to kilograms. We simply multiply by 100. A slightly more complicated example is changing Fahrenheit to Celsius. In this case, we subtract a constant and divide by 1.8. And you can see what this transformation does by looking at the common temperature scale. A key result is that the units of the newly transformed variable are regularly spaced with respect to the units of the original variable. This means that while the mean and spread of the data may change, the overall shape of the distribution will not. And you can see this here in a random sample of 1000 Fahrenheit temperatures I simulated and converted to Celsius. So the mean has shifted and the spread has narrowed as a result of dividing by 1.8, but the shape of the distribution is still the same. It's still symmetrical and it's still normally distributed. So z-scores, or as they're sometimes called, standard deviation or ST scores. So when a variable is normally distributed, it can be useful to convert it to a z-score. And the reasons for this are, first, it enables us to compare scores from normal distributions with different units. So for example, we may compare the height and weight from an individual using a z-score, or we may compare exam scores from a student across different subjects. Second, it allows us to calculate the probability of a score occurring within our sample. And this is the basis behind a reference range. Reference ranges have many applications. For example, we may wish to identify patients that have values from a blood test that are unlikely to occur if they're healthy. Often a threshold is used that identifies values that occur in less than 5% of healthy individuals. Monitoring childhood growth is another application. This allows us to estimate how big or small a child is compared to a reference population. So a z-score measures the distance of each observation from the mean in units of standard deviation. This is the equation. So for each observation we subtract the mean. That gives us the distance from the mean. And we then divide this by the standard deviation, giving us units of standard deviation, or z. A quick example. We've measured height in a sample of men. We find the mean height to be 170 centimeters with a standard deviation of 10 centimeters. So a height of 160 centimeters is 10 centimeters, or one standard deviation unit below the mean of 170 centimeters, and so has a z-score of -1. A height of 170 is exactly on the mean, so has a z-score of 0, and a height of 180 is one standard deviation unit greater than the mean, so has a z-score of +1. And just like the temperature scale shown earlier, you can also see how values map in a linear way from the original scale to the z-scale, meaning the shape of the frequency distribution does not change. All we've done is change the units. And so this new distribution has a mean of 0 and a standard deviation of 1. We can relate these z units to what is called the standard normal distribution, and this is a probability distribution. So here we've got a normal curve. The area underneath this curve represents the probability of observing z-scores of particular values. And so the total area under the curve sums to 1. We can look up the probabilities of obtaining z-scores as extreme as any nominal value we desire using statistical tables or a computer program. However, it's useful to be familiar with some of these values. One set of values perhaps worth remembering for making quick calculations in your head is the 68, 95, 99.7 rule. This runs as such. 68.27% of observations lie within one standard deviation of the mean, 95.45% lie within two standard deviations, and 99.7% lie within three standard deviations of the mean. Sigma is a Greek letter typically used to denote the standard deviation, and so this rule is sometimes called the 3 sigma rule. This rule can be used to make rough probability statements about observations. For example, there's less than a 2.5% chance that an observation selected at random from the population will have a z-score greater than 2. And these probabilities can also be directly linked to percentiles. For example, in a height growth curve that's normally distributed, someone with a z-score of 2 would be on the 97th percentile. So an example, in a large healthy sample of term babies born in Bristol, birth length and weight were found to follow a normal distribution with means of 50 centimetres and 3.5 kilograms and standard deviations of 2 centimetres and half a kilogram respectively. So what can we say about a baby born measuring 54 centimetres and weighing 3 kilograms? Well, this would give z-scores of +2 and -1 for length and weight respectively. And this allows us to see that this is a baby born long and relatively thin with respect to other healthy term babies born in Bristol. And also that this baby is relatively long for weight. So this example illustrates how z-scores can be used to compare against others in a population, and also how two variables that are both normally distributed can be compared on the same scale. And here's a list of terms introduced in this video.